Hi, and welcome back to a series I'm doing in complex analysis. Today I want to work with the following problem, which is easily stated, but in my opinion, kind of difficult to solve. So we have some function on the complex plane defined with complex values, which is injective and entire. So entire, I mean analytic on the entire complex plane. And we want to prove that f is linear, or in other words, f of z is really just some complex number a times its input z plus another complex number b. Okay, simple enough. But for this problem, we used two pretty advanced tools in complex analysis, which you might not expect. So the first tool I want to recall for you is the Casorati-Weierstrass theorem. And let's just take a look at that. So we have some analytic function on a punctured ball. So we have some point z naught, and maybe some radius epsilon, and then we have a poorly drawn punctured ball, and this is where our function lives. And z naught is an essential singularity of f, so the really crazy one. Then we say that the image of f on this punctured ball is dense in C. Okay, so that's a pretty powerful statement. And the second thing that we need to know is the open mapping theorem. So the open mapping theorem is a little easier to conceptualize if we just have some domain U, so maybe some open subset like this or something of the complex plane. And f is defined on U, it's non-constant and analytic on U. Then f is an open map, which just means that whenever we take some open subset of U, so maybe something like that, we take that to be our O, then the image of that guy that I just drew under our f is also an open set in C. So let's take a look at how those two tools can be used together later. But first, also for the same problem, we're going to need to be proving a lemma. So the lemma that we'll need is we need to assume that f is an entire function and that it has this limit, which is sometimes said that it has a pole at infinity. Then we can conclude that f itself is a polynomial. So kind of the trick to proving this lemma is to look at a function g of z so that we look at g as if it has a pole at 0. So let's write out kind of the power series for g. If it has a pole at 0, then we know that its pole has some multiplicity, call it capital N, and it might have infinitely many terms, and it has some complex coefficient Cn, and then Zn, just like any other power series, right? So g was cleverly chosen now so that when we look at f, we can write out f's power series. So f's power series then is really just kind of the reciprocal of that. So this is really a sketch of a proof. I'm not necessarily being super rigorous with this, but this is how you would prove it. I would rewrite out f's power series like this. But here's the problem. If these CNs are non-zero, right, then these infinite number of negative terms basically tells me that I have an essential singularity at 0. But we know f is entire. So that's not allowed. Not only does it not have an essential singularity, it doesn't even have a pole, which means that all those Cn terms for the negative numbers have to be 0, which means that really we can just rewrite our series, or our power series as this, which is just from the 0th term, the first one that's relevant, all the way up to the capital Nth term, which we still need. But already we're done. Because if we do that, then we've written out an expression for f where f is entire, it's equal to that everywhere, and that's a polynomial. So f itself has to be a polynomial. And so we've proved our quick lemma. All right, well, back to the problem. So f is injective, it's entire, and we want to prove it's linear. And somehow we want to use this Casorati-Weierstrass and open mapping theorems to say something about g, which is the same g I used here to prove this lemma. So let's take a look at two open balls. Let's say around 0 and around 2. And let's choose epsilon small enough so that these balls don't intersect, okay? Well then, g of this epsilon ball around 0 is dense in C by Casorati-Weierstrass, if 0 is an essential singularity. So if 0 is essential. So let's backtrack just a little bit. Remember, we defined G as f of 1 over z, so it has some issue going on at 0. We don't necessarily know what it is. It could be nothing. It could be a pole. It could be essential. So let's assume it's essential. And if we apply Casaretti-Weierstrass, we know that this is dense in C. Okay, well, what about the other ball? Well, by the open mapping theorem, this is open in C. But then these two things, a dense set and an open set, both in C, have to intersect. So these two things intersect. But remember, we chose these guys up here, we chose these guys such that they were disjoint. We chose epsilon small enough such that these guys were disjoint. But if these things intersect, then that means G is not injective. But that means F's not injective. And that's a contradiction. So off the bat, by using Casaretti-Weierstrass and an open mapping theorem, we can say something about the singularity that G has at 0. And that allows us to say that it's not an essential singularity. Okay, so we might already have kind of an inkling about what we're going to do based on kind of the previous lemma. If we can somehow say something goes wrong or that we can control this large N, then maybe we can say something pretty profound about F. Okay, so now we want to actually use our lemma. And like I said, we know that F, if it doesn't have this essential singularity, if it doesn't have this essential singularity at infinity, quote unquote, then it must have a pole at infinity. But the lemma implies that F is a polynomial. So F is a polynomial. And what do we know about polynomials? Well, the most basic thing we know is that we can apply the fundamental theorem of algebra to them, FTA. And this fundamental theorem tells us that we can write F as a product of these linear terms. So let's call it maybe AI, AIZ minus BI or something. And it's a polynomial, so we go maybe to capital N. And these AIs and BIs are just other complex numbers. So really these linear terms tell us what the zeros are of F. So we have really two cases. What if we had distinct zeros? So in other words, we had two complex numbers A and B, which are not the same, but are both zeros of F. But then off the bat, these are different numbers. They map to the same number. What am I hinting at? F is not injective. And of course, that's a contradiction, right? Because we suppose that F is injective. Okay, so if we don't have any distinct zeros, then we have only repeated zeros, which means that our expression above for F, we don't need the AIs anymore. Really, it's just the product n times of the same A's and B's. So it's the same zero repeated n times, however many times that is. So the derivative has degree capital N minus 1. Okay, so if n, capital N, if capital N is greater than or equal to 2, then the degree of f prime of z is greater than or equal to 1. And of course, it's going to have, the derivative will also have this as a 0, this b over a quantity, whatever that is. And that means that it's not injective at that point. So f, so because the derivative still has that as a 0, f is not injective in a neighborhood, NBHD, sometimes just neighborhood, of its 0. But that's also a contradiction, right? Because we already said that f has to be injective. Okay, so n can't be large, but that implies that capital N is really just 1. which if we look at our above expression, that really means that f of z is just az minus b. In other words, f is just a linear function.